Okay, where am I? Here it is. Okay, so, two functions unrelated to each other. And table of values, whether there is a formula behind it, it's not important. That's still what comes out. Okay, so, and then we paused, forgot about all of this, moved on to another function. This is sugar. Okay, so once again, time. Vertical axis, it's unlabeled, but you can certainly label it if you want to. That is the y-axis. So that's the difference is if we're planning ahead, we keep the axes labeled, and we know that the horizontal axis is t, the vertical label is x in the former case, in the latter case it is y. Okay, and then if we want to combine these two, we wanna that's what we did. So this graph, if I click on it, it highlights what data we used. Okay, so as you can see, we're not using t. The t information about t, so the information about when is gone here. We are only looking at the combinations of x and y. So wheat plus sugar, that is location on the xy plane. So careful here about trying to somehow combine these two functions to produce the third. That's not what's happening, right? So because if you just label the x's, you'll see that they really have nothing to do with each other label-wise. So let me make that picture. So if you have t and x, right, and it looked like this, and then we have t and y, and it looks like that. Okay, and the third one, it has x and y axes, and that choice is, by the way, is arbitrary. We could have called this x and that is y, and the graph is. Look at how intentionally I'm plotting it from right to left to follow the time. The time goes this way, and so naturally these two curves have order that simply coincides, not the order, the direction that coincides with the direction of the t-axis. Okay, so we're progressing from left to right because the t-axis points to the right. Here, even though I have these two indicated, they do not indicate which way time progresses. So either you're sitting and looking what's happening, how that dot, say a dot here, dot there, and how this point, say, progresses through the xy plane. That way you will know when you are. You know where you are. The information is here, x and y. That's your location, but you won't know when. Okay. So as I just showed you, that's roughly the graph. Let me try to copy it so it goes like this. Seemingly, right? And now you know the direction of the development. Okay. So ideally, what you do is you label the dots, the points on, say, this is, say, t equals 0. Look at it, x and y, there's no t, so that's why labeling might be necessary. And then here somewhere t is equal to 1, somewhere t is equal to 2, and so on. So that is the labeling of the parameter. Labels is the parameter. Okay. So the point of that is the very end. The point it came up. What is the point of this? It is the combined dynamics of the two quantities. There might be a dependence or relation or correlation about knows what else, but at least you are able to visualize that. And in the example that I made up, I changed the formula for the sugar, the second one, and the formulas appears to be similar, but otherwise you not necessarily can guess the exact relation between them until you plot it, and then the picture becomes very clear. And you can notice very clear that it is the dependence is linear. You can just, if you look carefully at all the points, not only they're on a straight line, you can figure out what that line is. And I'm not sure if it is clear. 1 and 3. So it seems to be going towards 0, but not all the way. And passing through 1, 3, which means that the graph is y equal 3x. Okay. So once again, if not in this example, but in that example. So that is more common, that you look at the picture and it doesn't really produce necessarily something that very revealing. But the dots help. What do those dots indicate? Proximity. Time interval. So in other words, you can figure out the speed. The speed, how fast you're going through the space. There is no space, but this is a space of prices, and that's how far they are developing. So starting point is over there, we're progressing this way, and even though there's a change in both prices, they are changing slower and slower, and that description I just gave is in fact a way to recover the original graphs. Right, so what I just said, that look at it, if I try to, suppose I'm moving from that point this way, I am, and then now suppose I'm looking at the x-axis separate, at the x-coordinates of these points, then what's happening? I'm here, then here, 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 here. Okay, so how do I describe it? Is that x is decreasing, slow and slow and slower. And it might be approaching 0. Okay, indeed, that's what we see about x. Okay. On the other hand, over here, same thing here, similar behavior you can discover about y. And well, this is a very simple situation. This is more example of what you can discover by plotting from this abstract situation. But really, this one is more challenging and more interesting to be able to tell, to see that actually just about all the information that those two functions contain is contained in this graph. Okay, so can you try to describe what's happening to x? How would you describe it?
Right to left is decreasing.
Yeah, it is decreasing, and can you once again look at how the x-coordinate is changing? It's
getting like a smaller interval.
It's smaller and smaller. Yeah, that's right. It's getting smaller and smaller. That is the what you can see. As long as you know the direction of the development, we know that's right to left. So we can say that the value of x is decreasing slower and slower. And if you can guess that there might be a continuation here, it might be a vertical asymptote. Okay, which means that once again there will be that the value of x not just decreasing, it is decreasing, and its limit is 0. Okay, what is happening to y?
Increasing then decreasing.
It is increasing then decreasing, right? So increasing and then decreasing. So up to the point of roughly 0.5, roughly to 0.5, it is increasing and then decreasing. So it is like it is almost literally 2 points of view. If you imagine that this is a picture like this. Okay, so maybe let me plot it. Okay, so this is the graph. Okay, so how do I discover? Well, probably I could do it with the Excel, but let's do it on paper first. So how do I discover behavior of x? I look at it this way. Okay, so the development is from right to left, and I'm roughly discovering that indeed that's the pattern of behavior. On the other hand, if I look this way, I will discover the behavior of y, ignoring the behavior of x. So I can see that how it moves from right to left, and then from left to right, and since the direction is from right to left, it means first increase then decrease. With Excel, I would just shrink. So for the x-axis, I could do this. If I want to ignore what's happening to y and concentrate on x, this is what's happening. So this is x, y is ignored, and you can see how points going from right to left, and they're slowing down. Okay, then similarly I do with respect to y. Okay, that is less, well, you need some room to see, but now you can see, right? So it goes up and then down. Okay, however, what you could also say more about it about how fast. It is a little bit harder to establish that from those dots, but you can see that it does appear to be more dots up there, which means that at the top it is slowing down, which is what we know about functions anyway. So we are recovering all the information about these functions from this. Yes.
Is there a way to tell from that graph that the time intervals are equally spaced?
The last one from here. No. I mean, hypothetically, I could have changed the time and add, I don't know, rather than add every time the same value as I did, I could add an increase or decrease the value, and then that information is lost, unfortunately. I don't think I would like to do that. Different. Were you asking about non-uniformity or about just the size?
Just the, I guess both. Yeah.
Yeah. So it is certainly natural to try to change this value and make it smaller for more accuracy, for example, or bigger to cover more ground. As far as making it smaller or larger, that is certainly messes up your visualization. And this is, let's face it, this is visualization. So the data is here, and this is for the first function, this is for the second function. For the third function is you have to actually do this in order to see what data is being used. So we did do that yesterday, is producing the new function. The new function, that parametric curve, is a function, and but not the function that we have known, right? Because you can guess what the input is. The input is the same; it is still t, but the output now is these points. So they are x, y, two outputs. So that's roughly how parametric curves work. So t produces x, t produces y, and then we combine them together, and t produces x, y. Okay? So it's a new kind of function. A function with not two outputs, that wouldn't be fair. It is a pair. A pair of real numbers, and the order matters. So if you say there are two outputs, that would seem to imply that it's 0, 1, 1, 0, it's the same thing. But it is a pair, and that's why we carefully plot them on the xy plane. Okay. Okay, so that is one angle. What we did, we took two functions, combined them together into a parametric curve, and plotted it. At this point, we can do all kind of analysis of it, but before we are not doing any calculus. So let's just hold on that. With calculus, let's just understand the curves first. So this is the direct problem, if you like, combining two functions into parametric curve. We have seen the opposite. If you remember, what is the opposite? You have a parametric curve. No, I'm sorry. You have a curve. You have a curve, and make it a parametric curve. So, and that's primarily our orbits, but you cannot see orbits, so that may not be very revealing. But suppose this is a road. We actually can't see a road, so it is a curve. Okay, and then what I do is I want to parameterize it. In other words, represent. So parameterize it. What does it mean? It means find a parametric curve follows this path. How would you do it? You have a road. How would you? What do you do with the road?
Could you measure it?
You could. Yes. Yeah. You measure it. What's the easiest way? Well, not the easiest way, but you will have to drive through it, pretty much. Okay. So you drive through it and record your location at every time. Okay. So this is the curve, and this is a car. And then you drive through it in any manner imaginable. There are caveats there, but pretty much you can almost pick any way you drive through it, and then record. So drive over this road and record locations. And what are the locations? They are XY. Okay, so you're recording when and where. Okay, you have a GPS and you have your clock, right? So this will be clock, and this will be the GPS. Okay, and that way, that is a parametric curve. That's why some books call it a parametrized curve. Starting with a real curve, and then introduce a parameter, and as a result, you have a parametric curve, which can be represented in a number of ways. It's the same road, but different people will drive different speeds, even different directions, and all of those will be parametric curves producing the same curve. So different drivers, same curve. Okay, so that's the kind of an inverse problem from what we started. Always, every time you solve a problem, at some point you have to go backwards. It's like differentiation, integration, or computation, solving equations, sine or cosine, well, all of those. So it goes all the way every time. So that's the inverse. So parametrizing the function, parametrizing the curve rather than finding the curve for our two functions that we represent. This will be x, this will be y. Okay? So, all right. So once again, I'm postponing all the calculus issues, but you certainly can think of, we discussed a little bit just now, what if we use the calculus concepts from calculus 1 applied to these two functions, to the two coordinate functions, or component functions, for x and y, and you can certainly know then to begin with, derivatives, right? So you know the derivative of x with respect to t, and you know the derivative of y with respect to t. You combine them together, and you can know something about this curve. So can you suggest any way to do it? So I have one point already marked, right? So suppose I know the derivative here, and for the same value of t, say it is, I don't know, 2. Doesn't matter. It's 2. And I know the derivative. Remember what the derivative is? Slope of the tangent line. Okay? So, and suppose it corresponds to this point over here. So these points, 2 points on the graph, they correspond to this point over there. Any connection between these lines? 3 tangent lines.
They're all negative.
Well, actually, that would be positive. So which is not entirely, shouldn't be surprising. Why shouldn't be surprising? 2 negatives give me positive. Yeah, you can imagine that if I pick this point over here, and you have negative and positive, I would be over here, right? And this one has a negative slope. So in other words, the two slopes are combined somehow to produce the new slope, and it is kind of done either not by adding or subtracting, but it appears to be either multiplication, but in reality it is actually division. So you divide, this one is dx dt, This is dy dt. Okay, and what's the third one?
dy over dx?
dy over dx, and what do you think it is equal to? Dy over dt divided by dx over dt. So you divide those two slopes to produce the slope of the new curve. Okay, you can certainly we will be concerned about not dividing by 0. Right. So if dx dt is 0, in other words, what's going to happen if dx dt is equal to 0? The computation fails. What does it look geometrically? Dx dt is equal to 0.
Vertical line.
The vertical line here, horizontal line there. Okay. So that will be a big topic. So this is the beginning of the calculus of parametric curves, and so we'll do quite a bit of it. And there will be other problems. There will be certain integration. One thing that you saw before was computing, say, lengths. I remember computing a length as an integral, length of curve. So we will compute length of parametric curves as well in a similar fashion. Similarly, from physics, we'll be computing, for example, work along a path going through a field of forces. Okay, so these are the topics we're going to discuss. But since this is an introduction, I want to do something else. And once again, staying away from physics for as long as we can, because at some point it will be very much looking like physics. We'll be talking about forces, and we'll be talking about work and energy and stuff like that. So, but I picked this example in order to be able to broaden the scope of applicability of these issues. And one is, once again, make it broader. These are the two things that we have considered. If we add to the picture, we add bread. So wheat, price X, then sugar, price Y, and then I add bread. What should I call the price?
Z.
Z. So suppose we don't know anything about the actual economics, but common sense. What does common sense tell you about the relation between these?
Probably a correlation between bread.
And the higher the price
What
of
about
wheat,
sugar?
the higher the price.
Oh, yeah.
Okay, so in other words, Z depends on X. The price of bread will depend on the price of wheat. It will also depend on the price of sugar. There is some sugar in bread, right? So there you go. So the price depends on the price of bread depends on wheat and sugar. Yeah.
Is Z always going to be dependent like that, or is it just because of this example?
It's an example. Yeah. I mean, if you just pick a point, Z, X, Y, Z. So is there dependence or not? It's all, we're just living and doing something in the three-dimensional space. All kinds of functions and different versions of calculus appear in this three-dimensional space, and this is just an example, and you just in a second you'll tell me what I'm talking about here. So Z depends on X and Z depends on Y. What am I talking about?
Surface.
The graph will be surface. Graph of what? A function. So what function am I talking about? A function of two variables. Say, I don't know, have capital X1. A function of two variables. The dependence is tricky a little bit every time you use economics or physics for that matter. There is issues that if an economist would walk in and they probably would be very displeased with this treatment, because they would say that, well, it doesn't really where's cause and effect? Does the bread depends on the wheat, or maybe the wheat depends on bread? The price of bread is how much people are prepared to pay for the bread. Therefore, that dependence determines the price of wheat and the price of sugar, and it works backwards. And then there is a feedback loop or something like that. So let's ignore that altogether and just look at it mathematically. And well, you can think of it as you are a bread maker, okay? And then you just decide decide ahead of time if the price of bread is this, if the price of wheat is this, and the price of sugar is this. I will set. It's entirely in my power to set the price for bread equal to this. That's the function, okay? That would be my choice. So it is possible to make a cause and effect function entirely dependent of z on x and y. So there is no feedback, there is no dependence, presumably. Once again, in economics, you can say wheat and sugar might be dependent on each other. So once again, we throw that out. I don't know anything. I am given the price of wheat, I am given the price of sugar, and I produce entirely my power to write down the price of bread as I choose it to be. Okay, so functions of two variables. It's very different in up to this point. Up to some point, will remain unrelated to parametric curves. There is no t, right? So I will be every morning. I look at the prices for wheat and sugar x and y, and use my formula that I devised to produce the price of bread z. Okay, so and we will reconnect these two later on. But at this time, this is the whole problem is right here, and we have shifted from parametric curves to functions of two variables just for a short period of time. And okay, so let's just continue with the similars, with example from before, and let's make up what would be a reasonable dependence or semi-reasonable dependence of what we have here. So we have to make up a formula. That's pretty much it. Okay, some simple formula. So what do you think the dependence is? What could be descriptively before we get to the formula?
It should probably involve a sum of x and y.
I mean, it is quite possible, yes. What I'm talking about is on a more basic level, just as we did over here. The price, the monotonicity. If the price of wheat increases, what does it do to the price of bread? It increases, right? Same with sugar. So x increases, then z increases, or simultaneously but separately, y increases, then z increases too. Okay, so the sum of the two certainly works. So you could, in hypothetically, you can say z is equal to xy. That probably would be a simple answer to come up with this function b c x plus y. But they're certainly disproportional. So I want just to complicate things so that our picture would be more interesting than just this. So maybe wheat is more important. Well, actually, why do how about I add 1? Why did I add 1? Because there are other things that may be involved, and so certainly when the price of wheat and bread is 0, it does not necessarily mean that the bread is there's labor, there's other materials. Okay, so I want to preserve these two requirements. Okay, but look at it, we want to make it look slightly different. So I'll just put 2 here. Suppose suppose wheat is more important. Okay, so this is my function of xy. As you can see, 2 functions appear to be appear separately. Now the tricky part is it is actually a slightly more complicated situation than parametric curves, because there are 2 variables. There are 2 variables and they vary independently. Okay, so 2 independent inputs. So this is the input now of our function, and this is the output. Okay, so at the end of the day, we'll have a surface for sure, but then let's examine slightly what is that we're looking at with data. Okay, so for example, this is f of xy, f of xy. Okay, So say, for example, f of 0, 0 is equal to 1, f of 1, 0 is equal to 3, f of 0, 1 is 2, f of 1, 1 is 4. Okay? So as you can see, you already can see how many more values we have to care about. And even though I tried to put it in the form of a list, well, it's not really a list, is it? If I want to produce more of these, will I continue with this list? I could, but you can see how I have to remember which one I have taken care of, which one I did not. So, meaning that the two are independent, and so I make sure that I have x is 0 twice, and it is 1 twice, and the same thing for y. So if I wanted more of these, let's suppose I want to try to have 3 values, say 2. So it will be f 0, 2, f, second, 1, 2, f, 2, 2. Okay, did I miss any? Did I miss any? No, I missed some. What did I miss?
2, 0.
No, 2, 2 is here.
2, 1.
2, 1, okay, so you can see how it's easy to miss. So by, because the x's and y's do not, x, y's pairs do not form a list. What do they form? They form a table, x and y. So I could put x is horizontally, 0, 1, 2, and I put y vertically, 0, 1, 2. Okay, so then, and then I'll put z's, and the rest will be z's. Okay, so 0, 0 is 1, 1, 0 is 3, 2, 0 is, I don't even have to look at the formulas, at those computations, look at the formula. So x is equal to 2, y is equal to 0, it gives me 5, right? Okay, and then if y is equal to 1, I have 4, is it? 4, no, 3. 3. Okay, no, hold on a second. No, x is horizontal. X is horizontal, so it will be 2. Sorry about that. 2, and then you can see the pattern. Then you will notice the pattern. What's the pattern? F of 1, 1 is 4. I add 2 as I move horizontal. Okay, and this will be 6. And if I move vertically,
And 1.
add 1, 3, 5, and 7. Okay, so this is the value of functions. Very much different from what we have seen here. The value of function, one variable, one output is what it looks like. If you combine, as we did with the into our parametric curve, it will be 3 columns: t's, x's, and y's. Okay, so it is still a list. This is not a list. Okay, so it is actually a table of values, and you can see how would, and then on and on, so certainly might continue on. You can imagine what, if we try to visualize this data, how would we do it?
Matrices in a calculator or computer?
Matrices?
Yeah, you kind of like a matrix.
No, I meant visualize, so this is a matrix. So how would you visualize the values of z that are listed here, while x's and y are respectively vertically and horizontal? Well, should they be vertically and horizontal, or should this be horizontal, like this? Right? And then the third dimension, how do I use the third dimension that now is available? I plot these numbers. I plot them as, say, bars, which is what Excel is good at. So I would plot, roughly speaking. So imagine, let me try. So imagine that this is like a piece of paper. Like this. It is a piece of paper. Okay, and then I plot z's like this. What happened? Where did it go? I think I lost it. And I don't think that this, I didn't push save, so this is all done. Here it is. Okay, I think I just jumped back. Okay, you have to push save once in a while. But, okay, so I plot a bar. I plot a bar. Red. I don't know, it just jumps arbitrarily. Okay, so 1, 3, 5 goes on like this. So imagine that is a thick bar. This is 2, and this is 4, and this is 6. Okay? And then this is 3, and this is 5, and this is 7. Okay? So it's when you do it by hand, you might not be able to entirely to recognize what's going on. But we already know the pattern, so we know that height, as it is moved towards us, the height increases by 1, so this is in fact a straight line pointing at us, and this one too, and that one too. Okay, and then you can combine them also with horizontal lines as well, going like this, going like this. Okay, like this. Okay, so, and that, not just a surface, it is specifically a plane. The graph will be a plane, which is very hard to discover from simply looking at these data and do it by hand, so that's why we're going to do it next with Excel. So, we're gonna come up with functions. We already have a function, okay, 2x plus 1 plus y. We'll take this function and we will plot it in this manner that we have here. So this will be a spreadsheet, and then we use a chart from Excel that will create a surface right about. So I we have some time left, so we're going to start on that. But I want you to also notice how much stuff is going on in this little table. It is in fact. Well, let me ask you, suppose this is the whole table that we have, like this. Suppose we don't have much else. How many functions do we have here? Functions from calculus 1, functions of one variable.
2.
All right.
3. A lot.
Oh, would it be 9?
6.
I believe it is 6. Each column, so this is the input, and these are potential outputs. That gives me 3, and then 3 more vertically. Okay, so that gives you 6 functions right away. And you produce more rows, more columns, and each of them is a function once again, in a function of one variable, input, output. So the outputs are the numbers. I could literally do what I just said, and I pick. This is definitely a function, right? X is a function of what? The input is y, and the output is z. Okay, not this one. Okay, so the inputs for y are 0, 1, 2, and the outputs for z are 1, 2, 3. So geometrically, it will be a cut of our plane, of our surface over there. They just plotted poorly. And we cut it with a plane like this, and what we end up with is a curve. The crossing of two planes, or two surfaces, typically a curve. Okay, so let's try to do that. This is a multi-step procedure, but we have a couple minutes left, so let me at least get started on this plotting something more reasonable based on this formula. So I will have to have x's and y's plotted separately to begin with, but in a manner similar to what we already had. So we will have axis going horizontally, y is vertically, and once again there will be, just as here, there will be step h. So let me get started with this. Okay, so I'll start with h once again, say 0.1. Okay, so here I will start x, so y slash x, indicating that to the right I will have a bunch of x's, and down I'll have a bunch of y's. Okay, let's start with 0. Okay, so what we did yesterday, now remember how we use Excel. I want to progress by 0.1 from 0, from 0, so I will just push this, plus what?
0.1.
What?
Row two,
0.1, yeah, but
Row two column.
C, row 2, C1, right? Row 2, C1. Okay, so that's the reference, and this is the inputs. These are just the inputs. It just takes some time just to produce the inputs. Control, okay, numbers. Okay. What happened? Did I do? Okay, okay, sorry. My mistake. Okay, so this is correct, and I just did it. Okay, so these are the values, and I do the same with y. I start with 0, and then once again right equal to previous value plus R2 C1 again. Okay? And once again I have a bunch of values of y. And then I will be entering formulas for the formula for f, which would have the formula for, and I have a bunch of values here in this square. Okay? So we'll do it next time.